in real time. This is a good panel that shows you how systems react to different impedances that you provide the microgrid. But you could also automate this, and this shows a good example of how testing can be done. So, for example, this microgrid is part of a larger 600 node distribution network. It has a battery energy storage system, a wind turbine, a PV array, and a few different kinds of loads. It's all controlled by a microgrid controller that implements two main functions of the microgrid controller. It's not a complete controller yet. We're just demonstrating two functions. One is planned islanding, and the other one is energy or power dispatch, ensuring a reference power that either injected or pulled, absorbed from the main grid. So right now we are at -6 kilowatts absorbing, injecting power. We can increase this reference to maybe 4 kilowatts, and we can see the battery energy storage system dispatch changed to respond to this. We can also provide different disturbances like load changes and see how the system reacts. We also provide, we can also reduce the wind speed, so the wind power goes down. We can slow down we can reduce the irradiation and see how the power reduces. So if we want to do planned islanding, we request islanding event, and we see the power over here reduces down to 0. That's what the controller does, and then the controller opens the breaker, and now we are running in islanded mode. We can also run different kinds of studies. For example, we can have a definite load profile, an irradiation profile, and a wind profile, which we can see over here. And we'll see once we activate that, it starts reading the irradiation, the load, and the wind speed data from a recorded previous day, which was taken from California ISO, and then we can see how the system performs, especially the battery energy storage system dispatch. I'll shut down the profiles here. We can also perform fault studies. For example, we can have a 3-phase to ground fault on one of. So right now we are seeing the 3-phase to ground fault on one of the nodes in the distribution network, and we can see how the battery storage system responds to that fault. So the fault results in a voltage sag on the microgrid, and therefore the current increases to maintain power, output power from the battery energy storage system. So another thing that we have over here is that we are simulating the power electronics of the battery energy storage system on an FPGA that runs at 1 microsecond time step, while the whole network runs at a 50 microsecond time step. With that, we can actually see the ripples on the current of a battery energy storage system, whereas the rest of the DERs will show you nice clean waveforms, because they are average model converters used to implement them. But for the battery energy storage system, we can see the current has a lot of ripples on them.